Today we're going to be talking about Riemann sums. Riemann sums are kind of the first dipping into integrals for Chapter 5. So Chapter 5, we are starting kind of a whole new dimension, whole new side of calculus. And today we're going to be talking about area. So if f is continuous and non-negative on the interval a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is represented by this, what we call a definite integral. That little swirly s with the a and the b on top, that is your integral sign. And then f of x dx is just the function we're actually integrating over. So integrals have to do with areas of regions. So while derivatives have to do with the slope of the curve, integrals have to do with the area under the curve. So they're kind of almost opposites of each other. We're going to explore that a little bit more as we come up. But with Riemann sums are a way to estimate this area without finding the actual integral. So when mathematicians were first kind of discussing the idea of integrals and the idea of finding this area under the curve, they used Riemann sums to estimate that area under the curve. And we're going to look at a couple of different types. So the first one is a left Riemann sums. And Riemann sums, they all have rules to them. You don't just get to randomly draw stuff. But a left Riemann sum says that I'm going to draw rectangles under my curve with the lefternmost point of the rectangle touching the curve. So here my left Riemann sum. As you notice, I draw my rectangle where the lefternmost point of the rectangle is what's touching the curve. So boom. Boop. And boom. And then all of this area of these rectangles underneath is going to be my estimated area under the curve. Now, some things that you'll probably notice right off the bat, it's not perfect, and it's not meant to be perfect. It is an estimate, and really in calculus, we use all these even though we know they're imperfect because we want to go through that same process of discovery with calculus. So some things you should notice with my left Riemann sum right now, I'm missing some of this area. So if we were to draw this and then we were to talk about our area, we'd say our area is an underestimate. We know it's not going to be as much as the actual area under the curve. Now, some other things we might talk about. If you notice, all of my rectangles currently are about a width of one x value. Well, if I made them skinnier, so if I did a width of like 0.5, all of a sudden, I'm not having as big of gaps in between my rectangles. My triangles have gotten smaller, so I'm missing less area. If I got them even closer, so now I have almost no gaps at all in terms of area I'm missing under the curve. So the smaller and smaller your rectangles are, the better estimate your Riemann sum is going to be. Okay, so two things to keep in mind about Riemann sums is they are estimates, so they are not meant to be perfect. And then the smaller your rectangles are, the better the estimate is going to be, just in general. So now if our left Riemann sum was the lefternmost point of the rectangle was touching the curve, our right Riemann sum is that the righternmost point is what's touching the curve. And so I just go across and draw my rectangles like so. And then all of that area under the curve is going to be my estimate. Now, with our right Riemann sum, you might notice, well, now we're getting a little extra area, these little pieces of the triangle that's up above. So once again, Riemann sums are not meant to be perfect. Okay, so this is going to be an overestimate if we were to compare it to what the actual area under the curve would be. And just like with our left Riemann sum, if we were to make smaller rectangles of smaller widths, we would have less and less of an overestimate until it got pretty close. Okay, let's finish up with the last two. So left Riemann sum was lefternmost point, right Riemann sum was righternmost point. Midpoint Riemann sum is middle of the rectangle. Oop. So this one can kind of be the hardest to draw because you have to kind of think about where that middle point is. But as you can see, the very middle of my rectangle is what my curve is going through. And once again, when you're just sketching it like this, y'all, it does not have to be perfect. When we actually do some examples, we'll talk more about how to make sure it is the correct area under the curve. And just like so. And then last but not least is the trapezoid rule. Now the trapezoid rule is a little bit different because it involves drawing trapezoids instead of drawing rectangles. So for the trapezoid rule, we're actually going to use 2 points. So we're going to touch the curve at 2 spots. My line drawing tool, not my rectangle. So boom and boom. And then draw our trapezoid from there. So right off the bat, you should notice your trapezoid rule is going to be a lot better than your left or right Riemann sums. Just like your midpoint was kind of the halfway between the left and right, your trapezoid does kind of the similar idea with a diagonal line at the top instead of that flat line. So as I go across, you'll probably notice that it doesn't even look like I'm missing any area under the curve. Now, even though my drawing looks perfect with my trapezoids, we should know that it is not perfect. It's just because this curve is so gradual that it looks pretty good, but I am still missing just a little bit of the area under the curve still. But trapezoid and midpoint are going to be significantly more accurate than your left or right Riemann sum. So let's go and practice actually doing this for a problem. So we want to find the area of the curve for number 2 for the function y equals negative x squared plus 16 with 4 equal width trapezoids on the interval 0 to 4. So if I have the interval 0 to 4 and I want all of my trapezoids to be the same width, then they need to be a width of 1. So from here, I'm going to start at 16. I'm going to touch my next point 1 over. So there's my first trapezoid. Then from 15, my next point 1 over is at 12. My next point 1 over is at 7. And my next point 1 over is all the way down at 0. And all of this is going to be my area under the curve. All of these trapezoids. So you can already notice in this one, a little bit different than the last one, you can definitely see that I am missing a little bit of area. So while it's a pretty good estimate, it's still not going to be perfect, and that's not the point for it to be perfect. So to actually find this area under the curve, I need to think of what's my area equation for a trapezoid. Well, the area of a trapezoid is equal to height times base 1 plus base 2, all divided by 2, because it's that 1/2 height times base 1 base 2. So I add those bases together, multiply by the height, so it's like I'm doubling my trapezoid, and then I divide it by 2 to account for that half of that actual giant rectangle that I create. So all I have to do is I have to go across and just add up all of these trapezoids together. Okay, now to make it a little clearer what the base 1, base 2, and the height is, I'm going to rotate this real quick. So I want you to see that in our picture, our height is actually this x distance that separates each of the trapezoids. That's the height of our trapezoid. Our base 1 and base 2 are the two y distances. So this is base 1 here. This is base 2 here, and then as I go through each, it just doubles up base 1, base 2. My height, though, the x distance, is always going to be the same. So let's actually start writing out. So my area is equal to my first height, so 1. Base 1 plus base 2 is 16 plus 15. All over 2 plus width is still 1, so 1. 15 plus 12, all over 2, plus 1, 12 plus 7, all over 2, plus 1, 7 plus 0, all over 2. And if I add all of that up, I do get 42. Of course, on a real exam, y'all, you probably wouldn't have a calculator for a question like this. So you do need to be able to do that math by hand. But for today, of course, you can type in your calculator to save you some time. And then we weren't told anything about units, but typically if this was representing a real world problem, there'd be some sort of unit. So I'm just going to add them on today, just so we know that with, we're talking about area under the curve, real world situations, we're more than likely going to be talking about some sort of units. So always an important thing to consider. Hey, let's look at number 3. So number 3, we want 4 equal width rectangles on the interval 0 to 8. So this time we got a larger interval, still 4 equal width rectangles. We're doing a midpoint approximation, so we want the middle of the rectangle to sit. And since we have 8 in total distance, 4 equal ones would be widths of 2. So I'm going to come in here with my midpoint. And let's see. So between 0 and 2, the midpoint would be 1. So at 1, we're all the way up at 9. Then from 2 to 4 at 3, we're at 1. Between 4 and 6 at 5, we're also at 1. And between 6 and 8 at 7, we are up at 9. So just off the bat, you're probably like, wow, Mr. Arbone, this is a terrible approximation of this curve. And it probably is. It's not going to be very close. It's going to be off by a lot. But that's the point. The point is just to follow what the Riemann sum tells you to do. In the coming days, we're going to talk about how to be more accurate with these areas under the curve. So our area would be, this time it's just the area of a rectangle, which is a significantly easier area to find. So our area of a rectangle is just base times height. Nice and easy. So for each of these, we're just multiplying the base times the height. So our area for our rectangle would be 2 times 9 plus 2 times 1 plus 2 times 1 plus 2 times 9. And multiplying that all the way up, and we do get 40 units, whatever they are, because I don't know. And that's our answer. So one thing I do want to caution you to against as well is, yes, we're talking about area, but because of how these integrals, what situations they might actually represent, I don't want you to just assume that it should be whatever the unit is squared because you found an area. We'll talk about this more later, but just know you can't automatically assume with an integral that the units are whatever it is squared. Okay? So just kind of keep that processing in your mind for a bit, and we'll talk about it more at a later date. All right, so those ones are how to find it graphically. Graphically is significantly easier than having to find it from a table, because from a table you have to think about it a little bit more, while from a graph you can just draw the picture. So number one, we want to approximate the value of the integral from 0 to 12 with 5 subintervals as indicated in the chart. So here's our chart all the way across, and then those are our y values. So one of the biggest differences here is, first they tell you 5 subintervals as indicated in the chart. They didn't say 5 equal intervals. So I'm just going to use the distance between these x values as my intervals. So notice I have 6 x values, which means I have 5 intervals. So sets it up perfectly. Then for each of the Riemann sums, y'all, you have to think about how that is actually going to touch the curve. So your left Riemann sum, the lefternmost point of our rectangle is what's going to touch the curve. So as I go across the table, I want to multiply my x distance by my leftern y value. So for each of these, I'm going to multiply that x distance by the lefternmost y value, which you notice I leave out that last y value of 17 because it's going to be the righternmost point on the curve, which my rectangle won't touch. So my left Riemann sum's area is equal to, and it's just a rectangle, so we just go across. So 3 for the distance between 0 and 3 times 0 plus 2 for the distance between 3 and 5 times 4. And then I just repeat the process. So 3 times 7, 2 times 10, and 2 times 14. And add that all the way up, and we do get 77 for our area. Once again, still want to be just tossing in units so we don't forget about them. All right, so next we're going to do our right Riemann sum. So our right Riemann sum is same idea. We're multiplying the x distance, but this time times the righternmost point. So notice instead, now we skip that first point and we get all the rest of the points. So just right off the bat, since I'm not multiplying by 0 this time, I'm probably going to have a bigger area. So our right Riemann sum, we have the area is equal to 3 times 4 plus 2 times 7 plus 3 times 10. And then just repeat all the way through. 2 times 14 plus 2 times 17. And our area would be equal to, add that all the way up, 118 units. So, not too crazy with the table, y'all. You just have to really think about the shape to know what to multiply by. All right, last but not least, we have our trapezoid sum. So for our trapezoid sum, we're still multiplying by that same x distance. That x distance is still going to be your height. But now, with my x distance being my height, I then need to multiply by both base 1 and base 2. So I'm going to add and double up on those y values as I go across. So for my trapezoid sum, our area would be equal to 3 times 0 plus 4 over 2 plus 2 times 4 plus 7 over 2 plus 3, 7 plus 10 over 2 plus 2, 10 plus 14 over 2 plus 2, 14 plus 17 over 2. And that does give us, if we add it all the way up, 97.5. So one last comment I do want to make about these, y'all, because you might be like, well, Mr. Arbone, I can just type that in the calculator and then pump out an answer. When you get Riemann sum questions like this, it's typically on a free response question. And on the FRQ, they're going to give you a point for writing out the Riemann sum and a point for getting the answer. So you do want to get in the habit of writing it all the way out and then just plugging it all in the calculator or doing all the math real quick and then getting that number out. So make sure that you can do both because if you just pump out the number and you don't write me the work, if it's an FRQ, I can't give you full credit. Multiple choice, obviously, you'd be fine, but any FRQ, I can't give you full credit. So that's something to keep in mind with Riemann sums, y'all. But that is our intro to integrals. Next class, we'll dive a little bit deeper. But thank y'all.